Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to gravitation. Previously we discussed the gravitational potential energy, the concept of gravitational potential energy of an object within the gravitational field. In this video we are going to extend that discussion and determine the gravitational potential energy of an object which is on the surface of the earth or near the surface of the earth. When it is the position changes with respect to that. Okay, so before that, let us just quickly review what is the concept of gravitational potential energy. So basically it is the capacity or potential of the gravitational force to do work, okay, to perform work through the gravitational force of attraction, the mutual gravitational force of attraction between two objects. So gravitational potential energy is the work done in bringing an object which is initially at infinite separation distance. Let us say we have two objects. We have the yellow mass, yellow sphere, and the white sphere. The white sphere of smaller size is initially at infinite separation distance outside the gravitational field of the yellow sphere. Under the influence of the gravitational force, the mutual gravitational force, in this case the gravitational force exerted by the yellow sphere and the white sphere, its position changes and slowly it enters the gravitational field and it attains a certain position. Let's say we bring the white sphere from infinite separation to point P. So the total work done in changing this position from initial infinite distance separation to final point P, that is called as the gravitational potential energy. That work done is called as the gravitational potential energy. And the gravitational potential energy of an object, it is unique for a certain position in the gravitational field. As the position of the two bodies it changes, the gravitational potential energy also changes. Let's say we have again the two mass system, capital M, small m, separated by a small distance, small r, let's say, not small distance, small r, the separation distance is this much. In this case, the gravitational potential energy of this small mass m, it is given by this, minus capital G, capital M, small m by r. So the potential energy is directly proportional to the product of the two masses, inversely proportional to the separation distance. Now, suppose we have again the mass m, it is at an initial position I, which is at a distance r1 from this yellow sphere. It is then moved to position F, the final point F, and it moves under the influence of the gravitational force. So this is the initial point, initial separation, and this is the final separation. So the change in potential energy, it is given by this, okay, delta U is equal to G capital M small m 1 by Ri minus 1 by Rf. Okay, so in this case it will be G capital M small m 1 by R1 minus 1 by R2, because Ri is equal to R1 and Rf is equal to R2. This is the formula. Now, how we can use it to determine the gravitational potential energy of an object which is on or near the surface of the earth. Okay, let us say we have earth, it has a mass capital M and it has a radius capital R, okay, and we have another object which is of very small size as compared to the size of the earth. Let us say we have a satellite of mass small m. Initially the satellite is on the surface of the earth. So the separation distance between Earth's center to the surface, the initial position of the object, the satellite, at position A, we can write it as Ri is equal to R, the initial position. This is the initial position of the object. Okay, this is the initial position of the object, the satellite. Then it moves a vertical height h up to point B, vertically upwards. This is the final position, and it is lifted by a height small h. Okay, so now the final position B, the separation distance is capital R plus small h. This is the final position RF. Ri is equal to R, Rf is equal to R plus h. Here the important thing is that all measurements are done from the center of the earth, because the concept of gravitation, the gravitational force, it is a central force which acts along the line joining the center of the two objects. That's why all measurements are from the center. So this is the initial position. Ri is equal to capital R, and this is the final position. Rf is equal to R plus h. So if we use this formula, the change in potential energy of the satellite as it moves from an initial position Ri to final position Rf, if we substitute the values, these values, instead of Ri we use R, capital R, the radius of the earth, and instead of Rf we use capital R plus small h, where capital R is the radius of the earth, h is the vertical distance above the surface of the earth. So in that case, when we substitute these values, we'll get this. Delta U is equal to G capital M small m 1 by R minus 1 by R plus h. Instead of Ri we have used capital R, instead of Rf we have used capital R plus small h. Now we'll take 1 by R common here, so we have capital G capital M small m by R, and we have 1 minus, we have multiplied R here in the numerator so that it stays the same in both LHS and RHS side. 1 minus R by R plus h. Now here what we have done, okay, if you see this part and compare it to this part, what we have done, we have divided R in both the numerator and denominator. So we have G capital M small m by R into 1 minus R by R is 1 by capital R 1 plus small h by capital R, 1 plus h by R. This, we get this. Okay, so it is capital G capital M small m by capital R into 1 minus 1 by 1 plus small h by capital R. Again we can write it as GMM by R into 1 minus 1 plus h by R to the power minus 1. Okay, 1 by something, it is to the power minus 1. Now here the important thing to consider here is that the height h, it is very small in terms of magnitude as compared to the radius of the earth. Okay, this height h is very small as compared to the radius of the earth. This whole thing is valid only when this condition is satisfied. When the height goes greater than the radius of the earth, this equation is not valid. It is only valid when the height is lesser, considerably lesser than the radius of the earth. So only then what we can do is we can apply binomial theorem here. Okay, 1 plus x to the power n. Okay, in that case, when height is considerably smaller than the radius of the earth, it will be 1 plus nx. Okay, so here it will be 1 plus h by r to the power minus 1, it will be 1 minus h by r. So we have substituted 1 plus h by r to the power minus 1 as 1 minus h by r. Everything else is the same. 1 plus h by r to the power minus 1 we have substituted as 1 minus h by r using binomial theorem, and this condition is satisfied. So 1 gets cancelled, minus minus, and minus minus h by r, it becomes plus h by r. So we have capital G, capital M, small h by capital R square. Now here we have to remember we derived the expression for acceleration due to gravity, where gm by r square, capital G, capital M, capital R, everything is capital. Universal gravitational constant, capital M is the mass of Earth, capital R is the radius of the Earth. Gm by r square, that is equal to small g, acceleration due to gravity. So we have this much portion, it is equal to g. So we have gmh or mgh. The change in potential energy is equal to mgh, small m, small g, h, where small m is the mass of the object within the gravitational field of Earth, in this case the satellite. Small g is the acceleration due to gravity. Small h is the height above the surface of the Earth, which is much lesser as compared to the radius of the Earth, capital R. So the change in potential energy is small m, small g, small h. So if we have, let's say, any object, it has a certain mass, let's say small m. So it is lifted upwards to a certain height, small h, above the surface of the Earth. So the change in potential energy, it will be equal to small m, the mass of the object, small g, acceleration due to gravity, which is acting downwards, and small h, which is the height above the surface of the Earth, or the height of elevation. Okay, so this is the concept of potential energy of an object which is on or near the surface of the Earth. Here we have used the same formula of change in potential energy because of change in position of the object. Here we have used Earth as the source mass, which is the source of gravitational field, and the satellite is the small mass which is influenced by Earth's gravitational force. So with the change in the position of the satellite, the potential energy of the satellite also changes. So using this formula, we calculated the potential energy of an object, in this case the satellite, which is initially it was on the surface of the Earth, then it was lifted upwards to a certain height, and this was the expression of change in potential energy of the satellite. Mass of the satellite multiplied with acceleration due to gravity multiplied with the height of elevation. Okay, so this is the concept of gravitational potential energy of an object on or near the surface of the Earth under the influence of Earth's gravitational force within the Earth's gravitational field. Okay, so this is the thing.